Let me give you another property of big O. So this is theorem 2. And I'll call this the monomial theorem. Okay, theorem 2 goes like this. So suppose that I've got a function that is a monomial. So this means t of n equals some constant a times n to the k. Okay, so it is the argument, it's n, raised to the kth power multiplied by a constant. Okay, and so here a has to be greater than or equal to 0, and k has to be greater than or equal to 0. Okay, what is this? Well, this is big O of n to the k. So what does this mean? It means we drop the constant, right? I can totally ignore constants when I'm thinking about big O. Okay, so what's my proof? Super simple with this one. So let's just let c equal a, right? And we'll let big N equal 1. And so what do we have? I've got a times n to the k equals c times n to the k, which is less than or equal to what? Less than or equal to c times n to the k, right? So I'm just being silly in my exhaustiveness here. But what I've shown is that this thing is less than or equal to this thing for all n greater than or equal to 1. So this for all n greater than or equal to 1. And so I'm done, right? I'm completely finished with the proof. Okay, so QED. Right. Therefore, this is big O of that. Done. All right, let's do a little bit more interesting one, one that's going to be similarly useful. So I'll call this theorem 3. And this is polynomials, and so this will use the previous two results, and it'll let us show something new and important. So this is polynomials. Okay, here's the fact. A1 n to the k1 plus a2 times n to the k2 plus, and I'll say ... plus am n to the km is the following. So this is a little bit awkward, but it's big O of n to the maximum of all the k's. So n to the power of max k1, k2, ... km. Okay, so if I have a bunch of monomials added together, what do? I pick the largest power. I drop all the constants and I pick the largest power. And so with this one, I'm going to ask for all the a's to be strictly larger than 0. The ai is strictly larger than 0. Okay, and if there's any a's that are 0, we'll just delete the term, right? And all the k's are larger than 0. Ki is greater than or equal to 0. Okay, so why is this the case? So I don't need to give you the full proof from the definitions. Instead, I can give you the proof from the actual previous two theorems. Okay, so what do I have? I have that, so let's call this t of n equals this. So what's my proof? Well, t of n is a sum of functions, right? T of n is sum of functions. Okay? Each of the functions is a monomial. Each function is a monomial. Okay, what does this mean? It means I drop the power. Right? So this means, sorry, not the power, the coefficients. So this means I can just ignore the a's. Because that's what the monomial theorem allows us to do. Ignore the a's, right? And this is from theorem 2. All right, so once I've ignored the a's, now I just have a sum. I have n to the k1, n to the k2, plus n to the k3, and so on. So now what does theorem 1 allow us to do? It allows us to take the largest one. Right? What's the largest function? It's just n raised to the largest of those k's. Right? So then by by theorem 1, the result holds. Right? Just pick the largest power. Okay. And there we are. We're done. Right? Once again, I'll draw the little box, the little QED box this time. Once again, we've proved the theorem. Right? We've proved that we can drop all the coefficients, it just comes from a previous theorem, and we can just take the maximum power in the polynomial. All right?